Again, welcome to DSRT 734 class. This is inferential statistics in decision making. So in this section, we're going to discuss our first topic in inferential statistics, which is sample distribution and then the central limit theorem. So in our previous lectures, almost 4 weeks now, we went through descriptive statistics and also probabilities. So this is our first topic, which is again the major section of our course. We can see the title of our course is Inferential Statistics, which we may go more details in this section of statistics, somewhere around 8 chapters. So again, our main objective is to go through the steps on how to find the sample distribution, also to verify their properties, also to interpret the central limit theorem, also apply the central limit theorem to find the probability of a sample mean. So first we start with the sample distribution. Here we say the sample distribution is the probability distribution of a sample statistics. Here when we mention statistics, we are not referring to the subject name, but rather the characteristics of a sample. So there's two terms we should know here. The characteristics of a population is called a parameter. The characteristics of a sample is called a statistic. Now, the characteristics can be the mean of the population or the sample or the standard deviation or any value that related to other population or sample is called the characteristics of the population and also the sample, which refer to again parameter is for population, statistics is for sample. Also, the sample distribution can be formed when samples of size n are repeatedly taken from a population. So a very simple example is we have a population of some items and the population is 100. We can decide to take a sample of 20 size 5 times without replacement, which means we're going to use all the population. And this is the concept of sample distribution. I have a population of 100 and I'm taking a sample size 25 items and 5 times. So example is given here. We have a population with the parameters mean and standard deviation, and we take 5 samples. Then the sample statistics here will be the S1 bar, S2 bar to S5 bar. So here we say the sample distribution consists of the values of the sample means of S1 bar up to S5 bar. So this will lead us to the properties of sample distribution of sample means. Here the first property said the mean of the sample means is equal to the population mean. And what we mean here is that the mean of the sample mean is equal to population mean only if we use all the population in our samples. So example is I have 100 items. I decided to take a sample again, 20, the size is 20. Now I'm taking a sample without replacement, which means I'm going to have 20, 25 times. So I have 5 samples and each sample size is 20. 20 times 5 is 100. And we have 100 population, we use all the population items. Now, if I find the mean of each sample, and later on, so this case, I'm going to have 5 sample means because we have the sample is 5. Now, if later on I find the mean of the mean samples, the answer will be the same as the population mean. And that's the whole concept here, that the sample mean is the same as, again, the population mean. That's if we take the samples and we use all the population. And the second concept is sometimes we use the term square root rule. And here what we're trying to say is that the standard deviation of the sample mean is equal to the population standard deviation divided by the square root of the sample size. So by looking at this formula, we can say that anytime the sample size increase, the sample population will decrease. When the sample size decrease, then the sample standard deviation will increase. And the sample standard deviation also is called the standard error of the mean. So there you have an example here. We have a population. The population values are 1357. They are written on the slips of paper and put in a box. Now here they say we should take 2 slips of paper randomly selected with replacement, which means when I take the 2 slips, I'll bring it back again after I use it, replace it back to the population. Now the first, they say we should find the mean, variance, and standard deviation of the population. So this is the population 1357. So this takes us back to descriptive statistics. To find the mean, I'm going to add 1 plus 3 plus 5 plus 7. And the answer will be 16. Then I'll divide by 4. So the mean will give us 4. Add all the values, divide by the population size, which is 4. Then to find the variance, we just have to subtract each and the mean from each value and square. So it will be 1 minus 4 square plus 3 minus 4 square plus 5 minus 4 square plus 7 minus 4 square. And that's the formula here. Square. Then sum, we had all the 4 values. Then when we had finished, we divide by the population size, which is again 4. And that will give us 5. And this is variance. Now to find the standard deviation, it will be the square root of the variance, so square root of 5 will give us 2.236. Now the next step, they say we should grab the probability histogram for the population values. So here we have a population size. First thing, we are trying to summarize the data. We find the mean, then we find the variance and standard deviation. Now we want to visualize the data, so we decided to grab the probability histogram for the population values. And this is what we get. Again, remember we have 1357, and each probability, this is randomly selected. So we are assuming since we have 4 items, we equally share it among the probability among them. So we get 0.25. So here we say all values have the same probability of being selected, because based on the question here, we say it's randomly selected. Let's go back to the question. The population value is given on a slip, then 2 slips of paper are randomly selected. So randomly selected means they all have equal chance of selecting. So since they all have equal chance of selecting, 4 items then need to be 0.25 each. Because we know total probability should be 1. Now C said we should list all the possible sample of size n equal to 2 and calculate the mean of each sample. So for example, we have 1357. So we can have 13, 15, 17, 35, 37, and 57. And that's what we have here. So we have 1, 1, 1, 1, 1, 3, 1, 5, 1, 7. Then we go to 3, 3, 1, 3, 3, 3, 5, 3, 7. Then we go to 5, 5, 1, 5, 3, 5, 5, 5, 7. Then we go to 7 because it's 4 value, 1, 3, 5, 7. So we take each digit to combine with the rest of the digit. Take a second digit, combine. So that will be our gain. And it should be 16. So we go into the possible. So here you can see that we are not doing replacement. And we use all the population. So the sample size is 2. And we have 16 samples. So those are the values. So the red values here is the sample mean for each sample. So here 1 plus 1 divided by 2 will be 1. 1 plus 1 is 2. 2 divided by 2. Then 1 plus 3 is 4 divided by 2. The size is 2, so we are going to divide always by 2. 7 plus 7 is 14 divided by 2 will be 7. 5 plus 7 is 12 divided by 2 will be 6. Now, we know the population mean. If now all the 16 values here, we had all these 16 values together and divided by 16, our answer will be 4, because we know the population mean was 4. Let's go back and make sure. Yeah, population mean was 4. So if I take all the possible sample from the population and I find each sample the mean, and then later find a sample of the sample mean, that's I'm finding the sample mean, or the mean of the sample mean, the answer will be the same as 4. So here now they say we should consider the probability distribution of the sample means. So here we have from 1 to 7. We have only 1, 1, 2, 3, and 5 threes, etc. Then we get the probability for each. Then find the mean, variance, standard deviation of the sample distribution of the mean. So we find the mean for standard deviation, and first of all, we find the range, then we find the standard deviation. This time we are using, we can see here, we are not using the population value. We are finding the sample. So the sample mean will be the same as the population mean based on the theory, but the standard deviation will change. So here we get 5 over 2. Why 2? Because again, the size of the sample. So this is the formula. The mean is 4. Standard deviation of the sample will be population sample over square root of 2, or the n, which is 2. So that will give me 1.581. Only here again, there's a the square root is not there, but the answer is correct. The answer is correct. This is again, we are looking for variance. When we are looking for the standard deviation, that's why we have to use the square root of n. But if I'm looking for the variance, this square root will be square here. So F said we should grab the probability histogram from the sample distribution of the mean. Now this will give us a normal distribution. This is one of the, I think this is our last rule now. In this concept, the sample distribution of the mean always we get the shape of a normal curve. So what we're trying to say is that if I have a population, whether the population distribution is normal or not normal distribution, it can be normal distribution or not normal distribution. But when we take the sample of the population, we use all the population items and we have our sampling. The mean of the sample, their distribution now will be normal. So that's why here we can see a normal distribution now. And that's the concept of central limit theorem. So central limit theorem also said, if the sample of a size n should be greater than or equal to 30, I draw from any population with a mean and standard deviation. So when we're doing this test, we make sure the sample size should be 30 or more. Then the sample distribution of the sample means approximate and normal distribution. So the greater the sample size, the better the approximation. So let's say we have a data and the data is a binomial distribution. But now if I'm able to find NPQ. N will be the sample size, P will be probability of success, Q is probability of failure. If the value is greater or equal to 5, we also can say that we are approximating binomial distribution to normal distribution. So we are approximating the probability distribution to normal because NPQ is 5 or more. By here also the central limit theory said, if n is greater than or equal to 30, I'll draw from the population with a mean and a standard deviation. Then the sample distribution of the sample means approximate a normal distribution, which we saw in the previous slide. Now, the greater the sample size, the better the approximation. So here we said that if the population itself is a normal distributed, then the sample distribution of the sample mean is also normal distribution. And if the population is not normally distribution, still the sample distribution will be normal distribution. So here we say in either case, the sample distribution of a sample mean has a mean equal to the population mean. Then the sample distribution of a sample means has a variance equal to 1/n times the variance of the population, and the standard deviation equal to the population standard deviation divided by square root of n. So this is what we said earlier, that again, as the sample size increase, the variance or the standard deviation of the sample will decrease. Now, when the sample size decrease, then the variance and the standard deviation of the sample will increase because the size of the sample decrease. So here we say that any population distribution, standard deviation is given, the mean always is a central. This can be any population distribution. But if the distribution of the sample mean n is greater than or equal to 30, then we have to approximate it to normal distribution. So a normal distribution, the sample size have to be at least 30 or more, and we can see our normal distribution. Here, it can be any population distribution. Then here also we say this is a normal probability distribution. We have the standard deviation and also the mean in the center. And distribution of the sample mean any n, we still have a normal distribution, but the location can change. Two things also we should know here with the normal distribution, which we discuss in probability when we are doing the normal distribution, is that the location will be determined by the value of the mean. And the spread of the data, whether the graph is shrink or wide, is determined by the standard deviation or the variation in the data set. If it's high, then the graph will be wider. So we have an example here. Here they say we have a telephone bill for residents of a city, and they have a mean of 64 and a standard deviation of 9. So a phone bills for residents of a city have a mean of 64 and a standard deviation of 9. So we random sample of 36 phone bills are drawn from the population, and the mean of each sample is determined. Find the mean and the standard error of the mean of the sample distribution. Then sketch the graph of the sample distribution of the sample mean. So first, we know the first theory. The mean of the population is the same as the mean of the sample means. So 64. Then the second standard error means the standard deviation of the sample is equal to the standard deviation of the population divided by square root of the sample size, which we know the standard deviation of the population, when we look at the question, is given to be 9. It's given to be 9. So we divide by the sample size was given to be 36. We divide by square root of n, 36. And that will give us 1.5. Then here we have a normal, but we can see how the graph is shrink. But the mean is the same, 64, and the standard deviation is very small, 1.5. So we have another example here. Here we say the heights of a fully grown white oak trees are normally distributed. So first keyword is normally distributed with a mean of 30 feet and a standard deviation of 3.5. Random sample of size 4 are drawn from this population, and the mean of each sample is determined. Now the question says we should find the mean and also the standard error of the mean of the sampling distribution. Then we should sketch the graph of the sampling distribution. So we know the first rule again, the mean of the sampling distribution is equal to the population mean. So we have the mean of sample distribution equal to population mean, and that gives us 90. Then we find the standard error of the mean, which will be the population mean divided by population standard deviation divided by square root of the sample size. So we have 3.5, which is our population standard deviation divided by square root of 4. So next, since the population is normally distributed from the question, the sample distribution of the sample mean is also normally distributed. So we get the mean is 90, but we can see there's a shrink here because the standard deviation reduced. Previously, the standard deviation was 9. So standard deviation was it? No, sorry, standard deviation was 3.5. But to find the here we say the standard deviation of the sample, which is the standard error, is the population standard deviation divided by square root of sample size, which will be 3.5 divided square root of 4. So we can see that again, the sample standard deviation is 1.75, whereas the population standard deviation is 3.5. So here we know the mean, and we know the standard deviation of the sample. So next is to transform the S bar to a z-score. So this will be the value minus mean of a standard error. So we get S bar minus mu, X bar, which is the sample mean, divided by the standard deviation of the sample mean. So another example given, the graph shows the length of a time people spend driving each day. So you randomly selected 50 drivers, ages between 15 to 90. What is the probability that the mean time they spend driving each day is between 24.7 and 25.5 minutes? So here they say we shall assume a standard deviation is 1.5. So we know the central limit theorem. The mean of the sample distribution is the same as the population mean. So that's 25. Then we find the standard error, that is the square root rule. And the sample standard deviation is equal to the population standard deviation divided by the square root of the sample size. So that gave me 0.21213. Then from there we know the standard deviation, we just find it. That means we have it already. So here we can say that the S bar will be between 25.5 and then 24.7. And this is how we get. So first S1, or which is the z-score, is the first sample mean minus population mean over population standard deviation divided by square root of n. So we get 24.7 minus 25 divided by 1.5 divided by square root of 50, which gives us negative 1.41. Then in the Z2, the second, we have S bar minus mean over standard deviation over square root of n. Again, we are using the X bar and the standard error, because here we are again dealing with a sample. So we are not using the population standard deviation, rather sample standard deviation. So when we do this calculation, we get 2.36. So we can see from our table, again, we solved this problem in our previous lectures. From our table, we can see we have 0.9909 minus 0.0793. 0.9909 will give us the 2.36. Then negative 1.41 will give us 0.0793. So this will be our P, 0.9116. So another question said a bank auditor claims that the credit card balances are normally distributed with a mean of 2870 and standard deviation of 900. What is the probability that a randomly selected credit card holder has a credit card balance less than 2,500? So this will be our S value. So it will be, we find a Z, it will be 2,500 minus 2870 divided by 900. So they say here you can ask to find the probability associated with a certain value of the random variable X. So we can see our 2,500 and 2870. So we can see the Z score again. We said it will be 2,500, the Z value, minus the mean 2870 divided by 900, which was again negative 0.41. Then we find the second part. So here, for example, after we go to the table from the left. So whatever we get, the table will be our answer. So 0.3409. We don't need to subtract from one or add or anything because it's from left to the value. And here we say you randomly selected 25 credit card. What is the probability that their main credit card balance is less than 2,500? So here we are asked to find the probability associated with the sample mean S bar. And the mean was 2870. And the standard deviation will be 900 over square root of 25 because we select 25. So the sample size is 25. And in the sample size of previous slide, the standard deviation is given to be 900. 900. So 900 over the sample size against 25. So we get 180. So our normal distribution will be the mean is 2870, standard deviation is 180. And S bar, probability of S bar, S is less than 25. Our question is the probability that the S value will be less than 2,500. So to go to the left, and we look for the P value, and the answer will be 0.0197. Now, there's a question saying that there's a 34% chance that an individual will have a balance less than 2,500. So here we know that there's only 2% chance that the mean of the sample of 25 will have a balance less than 2,500. Also, is it possible that the sample is unusual, or it is possible that the auditors claim that the mean is 2870 is incorrect? So again, this will be the summary of our first lectures in the inferential statistics. Again, here our main goal was to go through the central limit theorem and also sample distributions. So we saw almost this is the continuum of a normal distribution, the whole concept. So again, wish you the best and thank you.